is music? How would you define music? Something you enjoy listening to over and over? A song that you like?
I came upon a child of God. He was walking along the road, and I asked him, "Where are you going?" And this he told me. I'm going on down to Yasgur's farm. I'm gonna join in a rock and roll band. I'm gonna camp out on the land. I'm gonna try and get my soul free.
A melody that gets stuck in your head? A work for piano? For violin? Or for orchestra? Music is all that, but it can be so much more. Especially in the last 70 years, it has evolved greatly, thanks in part to the advancements of technology. The broader and most accurate definition one can give to music is that music is the art of sound. It's the art of putting sounds together. Composing actually means putting things next to each other and creating a work that evolves over time. These sounds can be vocal.
13 femelles jeunes, les œils sont lèvres jeunes, hellali. Hellali, 13 femelles jeunes, les œils sont lèvres jeunes, hellali. Lèvres jeunes, hellali, 13 femelles jeunes, les œils sont lèvres jeunes, hellali. Les œils sont lèvres jeunes, hellali, 13 femelles jeunes, les œils sont lèvres jeunes, hellali. Elles jeunes, les œils sont lèvres jeunes, hellali, 13 femelles jeunes, les œils sont lèvres jeunes, hellali. Hellali, 13 femelles jeunes. Jeunes, jeunes sont, jeunes là, jeunes les, jeunes 13 femmes. Hellali, 13 femelles jeunes. Hellali, 13 femelles jeunes, jeunes sont, jeunes là, jeunes là, les, 13 femelles jeunes, les, jeunes, jeunes.
instrumental, electronic, or even everyday objects, and the human body. But what is sound? What is sound made of? And how does that influence what we consider music and what we think that music could be? I invite you now to pay attention to the following sounds. Try to listen closely. You will hear the same note played on different instruments. First, the bass clarinet. Now, the double bass. And finally, the bassoon. Listen to the same sounds once more. Bass clarinet, double bass, bassoon. And, new addition, the same note on the piano. We're now going to listen to these four instruments mixed together, one after the other. We listened to four different instruments play the same note, and I hope you were able to distinguish the differences between them. I invite you to think about what made the sounds different from one another, what you think distinguishes these sounds the most. We'll come back to this later on. But first, we have to define what exactly a note is. What exactly is this A sharp 1, or an A4, or a C6? Let's listen to this A sharp 1 again on the bass clarinet. And now look at it, first as a waveform, and now as a spectrum. These two representations of sound are quite different and show us two completely different aspects of it. We are first going to examine the waveform. The waveform, as its name indicates, shows us the shape of the vibrations of the sound in time. Sound is, after all, a vibration that makes air molecules move. One could say that music is basically air sculpture, in the sense that it cannot exist in a vacuum, because if there is no air, there cannot be any sound. The vertical y-axis is the amplitude of the wave, meaning how wide the wave is at any given point, and it goes from 1 to -1. These values are the maximum that digital technology allows without distorting the sound. The x-axis is time. When a sound is more or less stable, we can distinguish that a shape on the waveform is repeated over time. By looking at the waveform, we can tell how loud the sound is, how complex it is, and we can also calculate its pitch if there is one. Keep in mind that not all sounds have a distinguishable pitch. So, by looking at the waveform, we can figure out what the repeated shape is. This shape is what we call a period, and it is measured in seconds, if not milliseconds, to be more exact. It is symbolized with a capital T. Once we have the period figured out and we know how long it lasts, we can now calculate the frequency of the sound. The number of times a period is repeated within 1 second is what we call a frequency, which is symbolized with an F. The mathematical formula is the following. frequency is measured in hertz. So when we say that we tune our instruments to A4, meaning 440 hertz, what does that 440 hertz exactly mean? This is what a frequency of 440 hertz looks like. If we zoom in on the period, we can see that it lasts approximately 0.00227 seconds, or 2.27 milliseconds. Knowing the frequency, we could have calculated the duration of the period using the F equals 1 divided by T formula. I invite you now to open the software Audacity and the file entitled Finding the Frequency. Now, as a short exercise, I invite you to look at this waveform. Could you calculate what frequency it is just by looking at it? Yes, you can. First of all, using the zoom tool, zoom in until the waveform is easily visible. Try to make out what the period is. What is the part of the waveform that is repeated? Using the selection tool, select the period, see how long it lasts in seconds. And then, using the formula, calculate the frequency. Let's go back to the other way of representing sound and take a look at a spectrogram. This is an A4 on the clarinet as a waveform. And this is the same A4 as a spectrogram. What do you see? What the spectrogram shows us is the content of the sound, the ensemble of all the frequencies one hears within it and that form this particular sound. The brighter and the thicker the line, the louder the frequency, and the thinner the line, the softer it sounds. For the spectrogram, the x-axis is still time, but the y-axis shows the frequencies. The lowest frequency, in this case 440 Hz, is called the fundamental, and all the frequencies above it are called overtones or harmonics. The fundamental frequency defines which note is being played, and the overtones are the ones that give at every instrument its characteristic sound color that we call timbre. The ensemble of the overtones is called a spectrum or a harmonic series. As we can see, the overtones seem all to have the same distance from each other. And that is exactly right, since they are all integral multiples of the fundamental. If our fundamental is 440 Hz, the first overtone will be 440 multiplied by 2 equals 880 Hz. The second overtone will be 440 multiplied by 3 equals 1320 Hz. The third overtone will be 440 Hz multiplied by 4 equals 1760 Hz. The fourth overtone will be 440 Hz multiplied by 5 equals 2220 Hz, and so on and so forth. Let us now listen to the same sound, first as we know it, and then adding its overtones one by one so that we can listen closely to how the sound is structured from the inside. First, the sound as a whole. Now only the fundamental. Fundamental plus first overtone. Fundamental plus two overtones. Fundamental plus three overtones. Fundamental plus four overtones. Fundamental plus five overtones. Fundamental plus six overtones. Fundamental plus seven overtones. Fundamental plus eight overtones. Fundamental plus nine overtones. Fundamental plus 10 overtones. Fundamental plus 11 overtones. You can see at the bottom of the screen how the waveform changes with every new overtone that is being added. There is an infinite number of overtones contained in the sound, but we are only going to stop at 12. This type of detailed analysis of sound is called a Fourier analysis. In mathematics, Fourier analysis is the study of the way general functions may be represented or approximated by sums of simpler trigonometric functions, meaning sine and cosine waves. Fourier analysis grew from the study of Fourier series and is named after Joseph Fourier, who showed that representing a function as a sum of trigonometric functions greatly simplifies the study of heat transfer. Since the study of heat transfer had to do with vibrations and waves, it was also applied to music and sound, since, as we said earlier, sound is made of vibrations. A Fourier series is a sum that represents a periodic function as a sum of sine and cosine waves, The frequency of each wave, or harmonic, is an integer multiple of the periodic function's fundamental frequency. Each harmonic's phase and amplitude can be determined using harmonic analysis. A Fourier series may potentially contain an infinite number of harmonics. Now we will listen to the sound again. And this time we will listen to the overtones separately, one by one. I want you to pay special attention to the evolution of the intervals the higher up we go on the harmonic series. Here is the fundamental. Now the first overtone. Second overtone. Third overtone. Fourth overtone. Fifth overtone. Sixth overtone. Seventh overtone. Eighth overtone. Ninth overtone. 10th overtone. 11th overtone. Once again, slightly faster, with each overtone cross-fading with each other. As we can see, and I hope hear, the higher we go up the harmonic series, the smaller the interval gets between two overtones, despite the fact the difference in hertz is always 440. If we put them on a musical staff and treat each overtone as a fundamental, as a note, we have the following notes. We can see that the curve that the notes form closely resembles that of a logarithmic function. Having said that, we understand that the frequency scale is linear, but the musical interval scale is not. This is why, when it was time to divide the octave into 12 equal intervals in order to calculate the frequencies of each interval, musicians and mathematicians had to use the following interval ratio, the 12th root of 2, where every frequency, if multiplied by the 12th root of 2, gives the frequency of the next semitone. As an exercise, I now invite you to calculate all the 12 semitones of the chromatic scale starting from A2 equals 110 Hz up until an octave higher, meaning A3 at 220 Hz. You take 110, you multiply it by the square root of 2, and this will give you A sharp. Then you take what comes out, the frequency of A sharp, you multiply that with the 12th root of 2, and you'll have B, and so on until you reach 220 Hz. You could now basically calculate the frequency of each and every note on a piano using this principle, and even tune your piano. Using the same principle, one could divide the octave into more than 12 equal parts, as one can find in some extra-European cultures. In this case, one should use the nth root of 2, with n being the number of chromatic steps one would want to divide the octave in.